Welcome back. Today's topic is binary insertion sort. And honestly, why search one step at a time when you can dramatically cut the confusion in half?
What makes binary insertion sort different from regular insertion sort?
It still maintains a sorted prefix, but it uses binary search to find the correct position for each new element.
And what happens after finding that position?
The larger elements shift one place to the right, and the current element is inserted into the gap.
So it's essentially a sorted prefix combined with binary search.
Exactly.
So we can conclude that binary insertion sort is a clever variation of standard insertion sort. It maintains a sorted prefix and uses binary search to quickly find the correct position for each new element. Once that position is found, the larger elements shift to the right, creating space for the current element. In short, the main idea is simple: a sorted prefix combined with the power of binary search. That brings us to an important question. What exactly is binary search?
Binary search is an efficient way to find an element in a sorted list. Instead of checking every element, it begins with the middle one.
What happens after comparing the target with the middle element?
If the target is smaller, we continue searching in the left half. If it is larger, we continue in the right half. This process repeats until the target is found.
So the easy way to remember it is middle, compare, choose a half, and repeat.
Exactly, and each comparison reduces the search area by half.
Now that we understand the definition of binary insertion sort and its basic idea, can we look at its pseudocode?
Absolutely. We already know that the algorithm maintains a sorted portion and an unsorted portion. Now, let's see how each step is represented in pseudocode.
Great. Let's go through it one line at a time. The first line is binary insertion sort, AN. What does this line represent?
It defines a procedure named binary insertion sort. A is the array that we want to sort, and N is the number of elements in that array. We will assume that array indexing begins at 0.
Does the algorithm create a second array?
No, it sorts the original array directly. This is known as an in-place sorting algorithm.
The next line says, for I from 1 to n-1. Why does the loop begin at index 1?
Because the first element at index 0 is already considered sorted. The loop begins at index 1 and processes every remaining element. At the beginning of each pass, the elements before index I form the sorted portion. The element at index I is the next element that we want to insert into that sorted portion.
So the sorted portion becomes larger after every pass.
Exactly. It grows by one element during each iteration.
The next instruction is key equals A at index I. What is the key?
The key is the current element that we want to insert into the sorted portion. We save it in a separate variable because its original position may be overwritten while other elements are being shifted.
Can you give me an example?
Suppose the array is 3, 7, 5, 2. If I is 2, then the element at index 2 is 5. Therefore, the key becomes 5.
So even if the value at index 2 is overwritten, 5 remains safe in the key variable?
Correct.
The next part says, find the insertion position using binary search.
That line is a comment. It explains the purpose of the next section, but the computer does not execute it. The next few instructions use binary search to determine where the key belongs in the sorted portion.
The first binary search instruction is low equals 0.
Low represents the left boundary of the search range. It begins at 0 because the sorted portion starts at index 0.
The next instruction is high equals I. Why is high set to I?
Because the sorted portion contains the elements from index 0 to index I-1. High is an exclusive boundary. This means index I is not included in the search.
Why don't we include index I?
Because index I contains the current key. Binary search should examine only the elements that are already sorted.
The next condition is while low is less than high. What does this loop do?
It continues binary search while there are possible insertion positions left to examine. When low becomes equal to high, the search is complete. That shared value becomes the insertion position.
Inside the loop, we calculate mid. The instruction says, Mid equals low plus high minus low divided by 2. Can you explain that simply?
Mid represents the middle index of the current search range. Another way to say the calculation is, start at low and move halfway toward high. Integer division is used, so any decimal part is ignored.
Can you give me a quick example?
If low is 0 and high is 3, half the distance is 1. Therefore, mid becomes 1.
Why not just add low and high and divide the result by 2?
That formula also finds the middle. However, the version used in the pseudocode avoids possible integer overflow in programming languages that use fixed-size integers.
After calculating mid, we check if the key is smaller than A at index mid.
Correct. This compares the key with the middle element of the sorted portion. If the key is smaller, its correct position must be at mid or somewhere to the left of mid.
Then we execute high equals mid.
Yes, this moves the right boundary to the middle index. We do not remove mid as a possible answer because the key might need to be inserted exactly at that index.
For example, if the sorted portion is 3 and 7 and the key is 5, mid may point to 7.
Exactly. Since 5 is smaller than 7, the search continues on the left side. High moves to the index containing 7.
What happens if the key is not smaller than the middle element?
Then the else section runs. This means the key is either greater than or equal to the middle element. The next instruction is low equals mid plus 1.
Why do we add 1?
Because the key should be inserted after the middle element. We have already checked mid, so the next possible position is mid plus 1.
What if the key and the middle element are equal?
In that case, the new key is placed after the existing equal element. This preserves the original order of equal elements and makes the sorting process stable.
Binary search eventually stops, and the next instruction is position equals low.
Correct. When binary search finishes, low and high are equal. That index is the correct insertion position for the key.
So if the sorted portion is 3 and 7, and the key is 5, position becomes 1.
Exactly. 5 belongs between 3 and 7, which is index 1.
The next comment says, shift larger elements one position to the right. Why is shifting necessary?
Binary search tells us where the key belongs, but that position may already contain another element. We must move the larger elements to the right to create an empty space.
The next line is, j equals I. What does j represent?
The variable j controls the shifting process. It begins at the key's original index and moves toward the insertion position.
Why do we shift from right to left?
Shifting from right to left prevents us from overwriting elements before we have copied them. If we shifted in the opposite direction, some values could be lost.
The shifting loop says, while j is greater than position.
This loop continues until j reaches the insertion position. Every element between the insertion position and the key's original index is moved one position to the right.
Inside the loop, we execute a at index j equals a at index j minus 1.
This copies the previous element into the current position. Suppose the array is 3, 7, 5. The key is 5, the insertion position is 1, and j is 2. We copy the value at index 1, which is 7, into index 2. The array temporarily becomes 3, 7, 7.
It looks like 5 has disappeared.
It has disappeared from the array temporarily, but it has not been lost. 5 is still stored safely in the key variable.
The next instruction is j equals j minus 1.
This moves j one position to the left. If j is still greater than the insertion position, another element is shifted. When j becomes equal to the insertion position, the shifting loop stops.
The final comment says, insert the key at its correct position.
At this point, the algorithm has created an empty space for the key. The final instruction is a at position equals key. This places the saved key into its correct location.
Let me summarize the pseudocode. First, select the next element as the key. Second, use binary search to find its insertion position. Third, shift the larger elements one position to the right. Finally, insert the key into the empty position.
Perfect. The simple pattern to remember is find the position, shift the larger elements, insert the key.
Great. We have now moved from the definition of binary insertion sort to understanding exactly how its pseudocode works.
In the next section, we can perform a complete dry run and watch the array change during every pass.
In the previous section, we learned how each line of the binary insertion sort pseudocode works. Now, can we perform a complete dry run?
Absolutely. We'll use the array 5, 1, 4, 2, 8, 3.
The array contains 6 elements, so n equals 6. Because we use zero-based indexing, the index is run from 0 to 5.
Correct. The first element, 5, is already considered sorted. Therefore, the loop begins with I equal to 1 and continues until I equals 5.
And during every pass, we follow the same pattern. First, select the key. Second, use binary search to find its insertion position. Third, shift the larger elements. Finally, insert the key.
Exactly. Also remember that the midpoint calculation uses integer division. If the result contains a decimal part, we ignore it. Let's begin with our initial array, 5, 1, 4, 2, 8, 3. The sorted portion currently contains only 5.
And the unsorted portion contains 1, 4, 2, 8, 3.
Correct. Now we can begin the first pass. In pass 1, the loop index I is 1. What is our key?
The key is the value at index 1. The value at index 1 is 1. Therefore, the key is 1.
Good. The key is saved separately, so it will not be lost when elements are shifted. Now we use binary search to find where 1 belongs in the sorted portion. What are the starting values of low and high?
Low is 0, and high is 1.
Is low less than high?
Yes, 0 is less than 1, so the binary search loop begins.
Now calculate mid.
Mid is 0 plus half of 1 minus 0. Using integer division, mid becomes 0.
The element at index 0 is 5. Now compare the key 1 with 5.
1 is smaller than 5. Therefore, high becomes mid, which is 0.
Low is now 0, and high is also 0. Is low still less than high?
No, they are equal, so binary search stops.
The insertion position becomes low. Therefore, the insertion position is index 0. Now we need to create space for the key. We set j equal to I, so j becomes 1.
Since j is greater than the insertion position, we shift the element at index 0 into index 1. That copies 5 one position to the right.
The array temporarily becomes 5, 5, 4, 2, 8, 3.
Then we decrease j from 1 to 0. Now j is equal to the insertion position, so the shifting loop stops.
Finally, we insert the key 1 at index 0. The array becomes 1, 5, 4, 2, 8, 3.
The sorted portion is now 1, 5.
We now begin pass 2. The loop index I is 2. What is the key?
The value at index 2 is 4. Therefore, the key is 4. The current sorted portion is 1, 5.
Good. For binary search, low begins at 0 and high begins at 2. Because 0 is less than 2, we calculate mid.
Mid is 0 plus half of 2 minus 0. That gives us 1.
The element at index 1 is 5. Is the key 4 smaller than 5?
Yes. Therefore, high becomes mid, which is 1.
Now low is 0 and high is 1. Since 0 is still less than 1, we calculate another midpoint.
Mid is 0 plus half of 1 minus 0. Using integer division, mid becomes 0.
The element at index 0 is 1. Is 4 smaller than 1?
No. Therefore, the else section runs, and low becomes mid plus 1. Low becomes 1.
Low and high are now both 1, so binary search stops. What is the insertion position?
The insertion position is 1.
Now we set j equal to I. Therefore, j becomes 2. Since 2 is greater than the insertion position, we shift the element at index 1 into index 2.
The value at index 1 is 5. After shifting 5 to the right, the array temporarily becomes 1, 5, 5, 2, 8, 3.
We decrease j from 2 to 1. Now j equals the insertion position, so shifting stops.
We insert the key 4 at index 1. The array becomes 1, 4, 5, 2, 8, 3.
The sorted portion is now 1, 4, 5. Let's continue with pass 3. The loop index I is 3. What is the key?
The value at index 3 is 2. Therefore, the key is 2. The sorted portion is 1, 4, 5.
We begin binary search with low equal to 0 and high equal to 3. Because 0 is less than 3, calculate mid.
Mid is 0 plus half of 3 minus 0. Using integer division, mid becomes 1.
The element at index 1 is 4. Compare the key 2 with 4.
2 is smaller than 4. Therefore, high becomes 1.
Low is still 0. Because 0 is less than 1, calculate mid again.
Mid becomes 0. The element at index 0 is 1.
Is the key 2 smaller than 1?
No. Therefore, low becomes mid plus 1, which is 1.
Low and high are now both 1. Binary search stops, and the insertion position is 1. Now we set j equal to I, so j becomes 3.
Since 3 is greater than 1, we copy the element at index 2 into index 3. The element at index 2 is 5.
After shifting 5, the array temporarily becomes 1, 4, 5, 5, 8, 3.
We decrease j from 3 to 2. 2 is still greater than the insertion position, so we perform another shift. We copy the element at index 1, which is 4, into index 2.
The array now becomes 1, 4, 4, 5, 8, 3.
We decrease j from 2 to 1. Now j equals the insertion position, so the shifting loop stops.
Finally, we insert the key 2 at index 1. The array becomes 1, 2, 4, 5, 8, 3.
The sorted portion is now 1, 2, 4, 5.
We now begin pass 4. The loop index I is 4. What is our key?
The value at index 4 is 8. Therefore, the key is 8. The sorted portion is 1, 2, 4, 5.
For binary search, low is 0 and high is 4. Calculate the midpoint.
Mid is 0 plus half of 4 minus 0. That gives us 2.
The element at index 2 is 4. Is 8 smaller than 4?
No. Therefore, low becomes mid plus 1. Low becomes 3.
Low is 3 and high is 4. Because 3 is less than 4, calculate mid again.
Mid is 3 plus half of 4 minus 3. Using integer division, mid becomes 3.
The element at index 3 is 5. Is 8 smaller than 5?
No. Therefore, low becomes mid plus 1, which is 4.
Low and high are now both 4. Binary search stops and the insertion position is 4. We then set j equal to I, so j is also 4.
The shifting condition asks whether j is greater than the insertion position. But 4 is not greater than 4.
Correct. That means no shifting is required. 8 is already in the correct position.
We place the key at index 4, and the array remains 1, 2, 4, 5, 8, 3. The sorted portion is now 1, 2, 4, 5, 8.
We have reached the final pass. The loop index I is 5. What is the key?
The value at index 5 is 3. Therefore, the key is 3. The sorted portion is 1, 2, 4, 5, 8.
We begin binary search with low equal to 0 and high equal to 5. Calculate mid.
Mid is 0 plus half of 5 minus 0. Using integer division, mid becomes 2.
The element at index 2 is 4. Is 3 smaller than 4?
Yes. Therefore, high becomes mid, which is 2.
Low is 0 and high is 2. Because 0 is less than 2, calculate mid again.
Mid is 0 plus half of 2 minus 0. Mid becomes 1.
The element at index 1 is 2. Is 3 smaller than 2?
No. Therefore, low becomes mid plus 1. Low becomes 2.
Low and high are now both 2. Binary search stops and the insertion position is index 2. Now we set j equal to I, so j becomes 5.
Since 5 is greater than 2, we copy the element at index 4 into index 5. The element at index 4 is 8.
After shifting 8, the array temporarily becomes 1, 2, 4, 5, 8, 8.
We decrease j from 5 to 4. 4 is still greater than the insertion position, so we shift again. We copy the element at index 3, which is 5, into index 4.
The array becomes 1, 2, 4, 5, 5, 8.
We decrease j from 4 to 3. 3 is still greater than the insertion position, so we copy the element at index 2 into index 3. The element at index 2 is 4.
The array now becomes 1, 2, 4, 4, 5, 8.
We decrease j from 3 to 2. Now j equals the insertion position, so shifting stops.
Finally, we insert the key 3 at index 2. The array becomes 1, 2, 3, 4, 5, 8.
And now the entire array is sorted.
Correct. The loop has completed all 5 passes. Our final sorted array is 1, 2, 3, 4, 5, 8.
Now let's quickly run the Python implementation of binary insertion sort. Our input array is 5, 1, 4, 2, 8, 3. Watch the output in slow motion and try to recall the sorting logic we've learned so far. Binary search sounds faster. Does that mean binary insertion sort runs in big O of n times log base 2 of n?
Only for its best case running time. To understand the complete complexity, we must separate the cost of finding an insertion position from the cost of shifting elements.
Where does the runtime come from during each insertion?
First, binary search takes O of log base 2 of I comparisons, where I is the size of the sorted prefix. The algorithm may then shift anywhere from 0 up to I elements.
So, across the entire list, searching adds up to O of n times log base 2 of n, while shifting can add up to O of n squared.
Exactly. The insertion position is found quickly, but creating the gap can still be expensive. How do the best, average, and worst cases compare?
In the best case, the input is already sorted. No elements shift, but binary search still runs for every insertion. Therefore, the best case time is O of n times log base 2 of n.
With randomly ordered input, roughly half of the preceding elements may shift on average. With reverse sorted input, every preceding element shifts. Both cases accumulate to O of n squared.
So, binary search reduces the comparisons, but shifting determines the overall growth. Can shifting really outweigh binary search by that much?
Yes. When n equals 256, the comparison estimate is approximately 2,048. However, a reverse sorted list requires 32,640 shifts.
That is roughly 16 times more element movement.
Exactly. This is why reducing comparisons cannot remove the quadratic worst-case running time.
What about space complexity?
The algorithm sorts the original list in place. It keeps only a constant number of variables, such as key, low, high, mid, and position. Because binary search is iterative, it does not require a recursion stack. Therefore, the auxiliary space complexity remains O of 1, regardless of n.
The input list itself occupies O of n storage, but that is not additional memory created by the algorithm.
We can conclude that binary insertion sort finds insertion positions efficiently, reducing the comparison work to O of n times log base 2 of n.
However, the algorithm must still shift elements. Therefore, its average and worst-case running times remain O of n squared.
In short, fewer comparisons, the same quadratic movement bottleneck, and only O of 1 auxiliary space.
Both algorithms are called insertion sort. What actually changes between them?
They insert and shift elements in the same way. The difference is how they search for the insertion position. Basic insertion sort scans linearly, while binary insertion sort uses binary search. Both algorithms maintain a sorted prefix, select the next key, create a gap, and insert the key.
So their element movement step is identical.
Exactly. Only the position search changes. Basic insertion sort scans one element at a time, while binary insertion sort repeatedly halves the search range.
How much work does each search require?
Basic insertion sort may inspect up to I preceding elements. Therefore, one search takes O of I comparisons. Binary insertion sort repeatedly halves the range. This reduces one search to O of log of I comparisons.
But after the position is found, both algorithms still shift the same elements. What does the complete complexity comparison show?
Basic insertion sort has a best case time of O of n because a sorted list needs only one comparison per iteration. The binary version shown here still performs binary search every time. Its best case is therefore O of n times log of n.
But both average and worst cases remain O of n squared, and both use O of 1 auxiliary space. How large is the comparison advantage?
When n equals 256, basic insertion sort can make 32,640 comparisons in the worst case. Binary insertion sort needs approximately 2,048 search comparisons. That is about 16 times fewer.
So binary search creates a major comparison advantage as n grows. Does binary search reduce the number of shifts too?
No. With reverse sorted input, both algorithms must move every preceding element before inserting the key. When n equals 256, both perform 32,640 shifts.
That unchanged movement cost keeps the average and worst case time at O of n squared. When should we choose each version?
Basic insertion sort is usually better for small or nearly sorted data because its best case time is O of n and it has little search overhead. Binary insertion sort is useful when comparisons are expensive because it reduces comparison count even though shifting remains unchanged.
And for general Python programs, we should normally use list.sort or sorted.
We can summarize the comparison in one sentence. Binary insertion sort improves the search step, not the insertion step.
It reduces comparison growth from n squared to n times log of n, but the number of shifts remains unchanged.
Therefore, both algorithms still have O of n squared average and worst case time, and both use only O of 1 auxiliary space.
Let us practice the interview questions most commonly asked about binary insertion sort.
I will explain the algorithm. its complexity, its stability, its implementation details, and the trade-offs interviewers expect us to recognize.
What is binary insertion sort?
It is an insertion sort variant that uses binary search to find the key's position inside the already sorted prefix. Binary search reduces the position search to O of log of I comparisons, but the algorithm may still shift up to I elements to create the gap.
Can you show one insertion step?
Start with the sorted prefix containing 2, 5, 7, and 9, and let the key be 6. Binary search compares 6 with 7, then with 5, and finds index 2. The algorithm shifts 7 and 9 to the right and inserts 6.
The final order is 2, 5, 6, 7, 9. Where exactly does binary search appear in the algorithm?
It searches the sorted prefix from index 0 up to, but not including, index I. The result is the insertion position. Using upper bound search means equal values are placed after existing equals. Combined with shifting only greater values, that keeps the sort stable.
What complexity answer should I give in an interview?
One binary search takes O of log of I comparisons, so all searches total O of n times log of n. For the full search version, best case time is O of n times log of n. Average and worst case time are O of n squared because of shifting. Iterative binary search keeps auxiliary space at O of 1. An early exit check can reduce the best case to O of n.
If binary search is logarithmic, why is the total runtime still quadratic?
Because finding the position and creating the gap are different costs. All position searches total O of n times log of n comparisons, but element shifting can total O of n squared.
The larger shifting term determines the average and worst case runtime. Is binary insertion sort stable and in place?
Yes, if the binary search returns the upper bound, so the new key is inserted after existing equal keys, and only strictly greater values shift. The iterative version is in place and uses O of 1 auxiliary space. A recursive binary search would add O of log of n stack space.
How does binary insertion sort compare with the basic version?
Basic insertion sort scans backward linearly, while binary insertion sort finds the position with binary search. This reduces total comparisons from as much as O of n squared to O of n times log of n. However, both versions still have O of n squared average and worst case time because their shifts are the same.
When would you actually choose binary insertion sort?
It is useful for small arrays when comparisons are expensive, such as long strings or objects with costly comparison logic. It is less attractive for large arrays or expensive element movement because shifting remains quadratic. It is also a poor match for linked lists, where binary search does not have constant time random access.
What implementation mistakes do interviewers look for?
The common mistakes are choosing the wrong bound for duplicates, forgetting to save the key, and mixing inclusive and exclusive search limits. Also state whether binary search is iterative or recursive, because recursion adds O of log of n stack space.
I should test empty input, one element, sorted input, reverse order, and duplicates. Give me the 30-second interview answer.
Binary insertion sort uses binary search to locate each key's position in the sorted prefix, reducing total comparisons to O of n times log of n. It still shifts array elements to open each gap, so average and worst case time remain O of n squared. With iterative search, it is stable when using upper bound, in place, and uses O of 1 auxiliary space.